currently currently working at machine learning and data intensive computing mining lab at RIT, advised by Dr. Thiu. Today, I will be giving a talk on regularized evidential deep learning models for uncertainty-aware learning from limited data. So this is the outline of the talk. I will first briefly introduce uncertainty quantification, its need, and then introduce the evidential deep learning framework, that is a framework for uncertainty quantification. Then I will present the learning issues in the evidential deep learning framework, introduce our proposed solution, that is the regularized evidential deep learning models. Then I will move on to experiments and results, so application to a future classification problem, and summarize the work. This talk is mainly based on our earlier work in ICML titled Learning to Accumulate Evidence from All Training Samples, Theory and Practice. So let's first start with the deep learning model. Deep learning models have achieved great success in many real-world problems, and they are trained with large amount of data. If we consider this illustrative example, where the goal is to differentiate between the cats, dogs, and mice, we collect data for each of the classes, train the model. So we basically first collect the label data, train the model. The training basically proceeds as we pass the input to the model makes some prediction. We basically compare that prediction with the actual level of the image, and that is used to compute the loss. This loss is used to generate feedback for the update. So this is how most of the supervised deep learning models work. We pass data, the model makes a prediction that's compared with some ground truth, and that's basically used to feed as a feedback for the deep learning model. So considering the example of cat, dog, and mouse classification, once the model are trained, they can be used for prediction. So how the model works is we pass input to the model, it outputs score for different classes. These are the probability scores that sum up to 1, and here the score for the cat class is greatest, so the model prediction is cat. Similarly, in this example, we pass a dog image, the model outputs greatest probability for the dog class, and the model prediction is dog. But what if the input is something that's quite confusing? For instance, in this cat versus dog versus mouse classification, what if input is something like this? This image looks both like a cat and a dog. In this case, the model should basically say, I'm confused. This looks both like cat and dog. It has both cat and dog features. Another case could be the input is neither a cat, neither a dog, or neither a mouse, maybe a fish image. So the model has never seen such images, and basically the model should say it's neither cat, neither dog, neither a mouse. It should basically say, I don't know. I have never seen such inputs. But the deep learning models are limited in being able to express whether they are confused or they don't know. That is, they are unaware of their lack of knowledge. So there are these two cases. The first case is the input is something the model does not know, whereas the second case is the model is confused between different classes. And to enable deep learning models with such behavior, where model is aware of its knowledge and lack of the knowledge, the uncertainty quantification, it can enable such behavior. Basically, uncertainty quantification can enable the model to say, I don't know for such cases that the model has not seen, and basically say, I'm confused for such cases where it's confusing. And in uncertainty quantification field, many methods have been developed. Among those methods, evidential deep learning is one of the most promising approaches Evidential deep learning is based on the theory of subjective logic. It's a principal theory, and it's quite computationally efficient uncertainty quantification approach. It can be extended to many state-of-the-art deep learning models, and extending the evidential deep learning framework requires minimal changes. Uh, so if we go back to deep learning models, the deep learning models take an input and output probability scores. So this is basically a graphical diagram of standard deep learning models. They take the input, they output the probability scores. But just based on this score, there is no mechanism to quantify the fine-grained uncertainty for these models. Uh, Now, the evidential deep learning framework, it improves on this model by introducing a higher order distribution. Instead of neural network outputting the parameters P, it's basically outputting parameters for a higher order Dirichlet distribution. And this higher order distribution is what enables fine-grained uncertainty quantification. Uh, so something like in this evidential framework, we pass the input that is transformed to evidences. These evidences are transformed to parameters for of this Dirichlet distribution. And this distribution is what enables the uncertainty. Uh, so to better understand how it can express the two uncertainties, I don't know and I'm confused, let's get back to the original example. So for a cat input image, it can basically output high evidence for the cat class, zero or low evidence for the other classes. And if the output is something like this, then the Dirichlet distribution becomes something like this. So it's sharply peaked at the, the target class, that is the cat class. This is the visualization of the Dirichlet distribution, and since it's sharply peaked at one of the classes, the model is quite confident that the input is a cat. So this is one instance where the model is confident in its prediction. There is not much of confusion. So here basically the model is saying, I'm confident that it's a cat. For our original issue, that the input was quite confusing, containing features from multiple classes. This evidential model, it can output high evidence for multiple classes. This translates to a sharply peaked distribution, but that's not centered at corners, but at between some of the classes. So here what the model is saying is, the model is confident in its prediction, but it's confused. So it's basically confused between the cat and dog, but it's confident that it's confident on its decision. Now for the fish case, the model could output low evidence for all the classes. This would basically translate to a uniform distribution over the simplex. Something like the distribution would be flat, and this would translate to no confidence in its prediction. There is confusion, but basically there is model is not at all confident in its prediction. So basically model can say, I don't know, using these evidences. So in this way, like the evidential deep learning framework, it can enable fine-grained uncertainty quantification capabilities. In the first case where the model is confident and is not confused, it can output high evidence for one of the classes. And this basically translates to the vacuity and dissonance. These are metrics in evidential deep learning to express its confidence and confusion. High vacuity means that model is not at all confident. High dissonance means model is highly confused. In the first case, the vacuity is low, dissonance is also low. So it's not confused and it is confident. In the second case, it can output low evidence for all classes. That leads to a flat distribution and a very high vacuity. What this means is, even though the model is not confused, it's not at all confident in its prediction. it's basically saying, I don't know. In the final case, the vacuity is low. That is, the model is confident, but the dissonance is high. So the model is highly confused. That is basically it's a sharply peaked distribution that's between the uh, two classes. So, uh, so if we want to extend evidential models to the deep learning framework, we basically pass the input through the model and transform the model's outputs through some evidential activations to obtain the evidences. Uh, these activations, these evidential activations have some properties, and some popular choices used in literature are ReLU, soft exponential functions. What what these functions do is basically transform the output of the network into the evidence. From this evidence, we can obtain the Dirichlet parameters and look at the model's uncertainty. Moreover, the evidential models are trained with uh, specially designed evidential losses with incorrect evidence regularization. The model's training consists of two parts. First is the evidential loss. Second is the incorrect evidence regularization. And these two losses are balanced with a hyperparameter, that is the regularization coefficient, that balances the two parts. A lot of different variants of the loss have been developed, such as the Bayes risk with sum of square loss, Bayes risk with cross entropy loss, and type 2 maximum likelihood based loss. Different losses, different hyperparameter choices have been tried to train the evidential model. And, with the choice of activation and losses, the fine-grained uncertainty can be obtained from the evidential models. So we carried out experiments with evidential deep learning models, and what we found out was when we tried to scale the evidential models to a large-scale dataset of CIFAR 100 using a ResNet 12 model, we observed that even though it has good uncertainty quantification capabilities, its performance is quite low compared to the standard models. There is a big gap between the standard models and the evidential models. These standard models don't have the uncertainty quantification, but their performance is quite high. Whereas the evidential model's performance is almost half in one of these settings. Next, we tried to look at another experiment where we designed a two-way dataset that just has 4 data points. We modified the architecture uh, and looked at the evidential model's performance. The data had just 4 points, and standard model, it was able to easily overfit the 4 data points, obtain good accuracy. The evidential model was just able to obtain 50% accuracy. So what we observed was modifying the architecture could lead to failure of evidential models. Next, what we observed was the evidential models are trained with evidential losses with some regularization, but the models are quite sensitive to the values of the hyperparameters. Something like these three are 3 different variants of evidential model. The black solid one is the standard model, and all 3 models break with large evidence, the large value of the hyperparameter. One interesting thing to note is that without this hyperparameter value, the uncertainty does not become too meaningful. Like, we want the model's most confident predictions to be accurate, but if we do not use the incorrect evidence regularization, the uncertainty becomes untrustworthy. So to enable the uncertainty to be trustworthy, we need regularization. But with regularization, the performance, it was dropping significantly. Next, we also looked at the adversarial setting, and with strong adversarial attacks, the performance of evidential models dropped. But if we do not use any regularization, then the uncertainty does not increase. So to enable good uncertainty behavior, the regularizations are needed. So there seems to be a trade-off between the uncertainty and the model's performance. We wanted to investigate why this problem is there. That is, why the evidential model is giving such inferior performance. And uh, to this end, we carried out theoretical analysis of the evidential framework. And what we found out was, like, given a training sample, if the evidential model outputs zero evidence, then the gradients of the evidential loss evaluated on the training sample just reduced to zero. What this means is, like, if there is any sample in the training dataset with zero evidence, then the model is not at all able to learn from it. Mm. Uh, Here is one illustrative example to show what this means. So consider we have the training data. The model is trained with these cat images, and we have a new cat image that is quite different from the existing training images. The model basically outputs zero evidence for such training data. Basically, the model says, I don't know, I've never seen such data. And even though we provide the ground truth label that this is cat, the model is not able to update itself. So it continues to say, I don't know, and stops learning from such data points for which the network outputs zero evidence. Uh, and that was exactly what was happening in this two example where we modified the architecture. Due to modification in the architecture, the two of the samples, they were mapped to the zero evidence region, and the model, it continued to output zero evidence for those samples, and the model was not at all able to learn from those samples. Intuitively, if we visualize the learning of evidential models, then uh, this is for a two-class classification setting. We ideally want all samples of class 1 to be mapped in this region where the evidence for class 1 is high, and we want all the samples of class 2 to be mapped to this region where the evidence for class 2 is high. And the models updates to basically try to learn to map these samples. But if the samples are mapped to the zero evidence region, it just stops learning from them. The model basically learns based on the gradient signal, and for the samples that lie in this region, the gradient is just zero. So there is no update or learning from samples in this region. So what we observe is the model, it fails to learn from all zero evidence data samples. So any sample in this region, the model cannot learn. And this basically explains the earlier observations where we see the failure of evidential model with the architecture choice, the hyperparameter choice, and the datasets choice. So if our architecture choice is good enough that the model can avoid the zero evidence region, the evidential models may work. Similarly, if we carefully select the hyperparameters, the model may work. But the models are not at all robust. In the evidential setting, we have the evidential activation and the evidential losses. So next, we try to understand the impact of these activation and the losses to the learning of the evidential model. First, let us look at the evidential activation function. Uh, uh, in the literature, mainly three choices of evidential activation functions have been explored. That is the ReLU function, the surplus function, and the exponential function. So what these functions do is transform the output of the model into the evidences based on which the model has uncertainty behavior and the learning occurs. So we tried to see which one should we choose so that the model can learn better. And we again carried out a thorough theoretical analysis, whose proof is in the paper. And what we found out is that for a data sample, if the evidential model outputs low logits, that is, uh, the sample is mapped near to zero evidence region, then the update from the exponential activation function is larger than the surplus based function, and this update is larger than the ReLU based function. What this means is the training of evidential models is expected to be more effective with the exponential activation function. But so what this means is exponential activation function is better, but this does not solve the original problem. The exponential based model can still suffer from the zero evidence issue. Next, we tried to analyze the evidential losses, and uh, we basically consider the three most popular evidential losses used in the literature. Those were the evidential MSE loss, evidential cross entropy loss, and evidential log loss. We carry out analysis of all the losses, and what we find is for the evidential MSE based loss, it's a bounded loss that is just bounded in a small range of 0 to 2. No matter how wrong the model is, or uh, for any sample, it would just be the loss would be bounded in a small range, and it's better to avoid it. Uh, for other two losses, we basically found out that a reasonable learning behavior could be expected from these two losses in the high evidence region. But the losses, they would not be able to solve the original issue, that is failure to learn from the zero evidence region. So we basically analyze the weakness of evidential models, that is any sample that is mapped to this zero evidence region, the model is not at all able to learn from this region. So this is a problematic region, and we basically thought of pushing the data samples out of this region. So if a sample is mapped to this region, if we could just push it outside this region, the evidential framework could enable the model to learn from those samples. So for that, we wanted to design a regularization that could just push the samples outside this region. Once the samples are out of this region, the evidential framework can enable accurate learning, and the model's uncertainty would be reasonable. Learning would also be reasonable. So to enable such learning behavior where the model can map the samples outside this zero evidence region, we introduce a novel regularization function. This regularization function, its gradient is, if we look at the gradient of this regularization, it's not zero. It's based on the hyperparameter lambda. For the existing evidential models, the gradient was just becoming zero in this region, leading to the issue. But with this regularization, the gradient is uh, basically the hyperparameter we introduce. So it can enable the model uh, to learn from the zero evidence region. But once the sample is outside the zero evidence region, we want the evidential frameworks to update the model. So we basically set this hyperparameter based on the evidence. If the evidence is zero, this hyperparameter is one. And as the evidence increases, the hyperparameter value decreases, and the evidential framework enables the model's learning. And we theoretically show that this correct evidence regularization can address the learning issue. It can enable the model to learn from the zero evidence training samples. With this, we carry out experiments across multiple datasets and settings. And the first is the comparison on standard benchmark datasets. And we observe that our model performs significantly better compared to all other evidential models, because this can enable the model to learn from all the training samples. Next, uh, the evidential models, they were quite sensitive to the hyperparameter values, and their performance was quite suboptimal with the choice of the hyperparameters. Our model, highlighted in red, is significantly more robust compared to existing evidential models. So with the hyperparameter choice, the model is not breaking. The same can be seen in the right figure, where the proposed evidential model, it performs better compared to the baseline evidential model. Uh, Next is the impact of the evidential loss. We analyzed the three evidential losses, that is the evidential MSE loss, the evidential cross-entropy loss, and the evidential log loss. We had observed that the MSE-based loss, it was bounded, and that basically led to lower test set performance compared to the other losses. Our proposed regularization is quite agnostic to the choice of the loss, and it can enable the model to learn from all the samples. So it works with any of the evidential losses, uh, and it improves on all the settings. Next, if we look at the uncertainty trends of the new model, it continues to remain meaningful. The first figure basically shows the uncertainty behavior for different hyperparameter values, and the vacuity is the measure of lack of confidence. So lower the vacuity, more confident is the model. And on the most confident samples, the model should be more accurate. That is exactly what we observe for our evidential model. And if we try to look at the model's accuracy on top K% of the confidence samples, our model is quite good. It's quite accurate on the most confident samples, and it performs better overall as well. We next looked at application of our model to a challenging few sort classification setting. So few sort classification setting is basically we want to learn based on limited number of samples. For instance, here is a three-way two-sort classification task. What this means is there are three classes, and each class just has two examples. And just based on these six examples, the model has to become an accurate classifier, and it would be evaluated on new samples from these classes. And towards few sort classification, vision foundation models have been developed, and these models have been pre-trained on a large amount of data from which the models have acquired a lot of knowledge. Uh, so in this work, we looked at the visual prompt tuning. The BPT models are pre-trained on large data, and to fine-tune on challenging few sort, the backbone is kept frozen, a prompt layer and the head layer is fine-tuned on the data. So this is the standard BPT model. We transform this into the evidential model where we replace the head with a evidential head uh, that basically can transform the model's output into evidence, and we train with the evidential losses. We consider much CIFAR 100 data set and challenging 100-way one sort and 100-way five sort classification problems. Since this is a few sort classification problem, we also augment the data with some random crop and some horizontal flip. Then we carry out experiments for one sort and few sort for different regularization parameters. If we look at the basic evidential models, its performance is suboptimal. The regularized evidential model, it improves over the evidential models significantly across all the settings and the hyperparameter values. And this improvement is mostly due to the model it can learn from all the samples, and this leads to a significant improvement in the performance. So this was our work. We basically improved the learning capabilities of the evidential models, enabling the evidential model to learn from all the training samples. And some potential extensions of uh, this work are we enable the model to learn from all the samples, but the uncertainty metric it's relative. So it's kind of dependent on the strength of regularizations, and like stronger regularization can impact the value of the uncertainty. Relatively, the uncertainty is meaningful. That is, if a sample has higher uncertainty, uh, the model is likely to be wrong on such samples. But this dependent on the strength of regularizations, this is one limitation, and a possible future work would be to try to address this limitation. Second is uh, the extension to large language models and language vision models. So one of the issues with these large language models is they can basically hallucinate, or the outputs they give, they may not always be trustworthy. So we basically want to build trustworthy models with fine-grained uncertainty. So if we could extend uh, the evidential framework to these models such that the models can express whether they are outputting with confidence, and if the models could be accurate, or like if they are wrong, then basically say like I'm just guessing the answer, or I don't know this answer, then that could be quite useful. So one extension of this work could be like extension to the large language models and language vision models, and this is something we are actively pursuing in our lab. So with this, the key summary of the work is the standard evidential models, they cannot learn from data samples that are mapped to the zero evidence region, and we develop a novel method that can uh, address this learning issue. The proposed model is quite robust to the choice of the losses. It enables learning from all the samples and enables the framework to be extended to challenging datasets and settings. A lot of interesting extensions and applications are possible for this framework, and that's the end of the presentation. Thank you. Any questions? Yeah.
I wonder if you could just help me understand a little bit better about the basics of how these